Hello students, welcome to lecture 15 of the online course on introduction to microwave and optical metamaterials. In this lecture on concept behind metamaterials, we will be covering the following topics. So, we will look into metamaterials where engineering of the field matter interaction takes place, and we will go across metamaterials, how they are built, what are the basic concepts, how do you classify them, and also how do you classify engineered materials by size and frequency. So, when we talk about metamaterials, these are basically engineered materials which are allowed to customize your electromagnetic wave and matter interaction, right. So, it is basically a structure designed to manipulate how fields, you can take electromagnetic fields or even acoustic waves, they interact with matter. So, you can grasp this concept with a simple analogy. So, you just imagine standing in a field of tall grass on a breezy day. So, you will see that as the wind blows, each blade of grass sways in response to the strength of the wind and its direction. So, although the wind itself is invisible, a dispersed stream of gas, which is the vibrations in the molecules, or vibration in the gas molecules, you can say, they can exert a force that we all can feel, right. Now, a physicist might describe this wind as a vector field which is continuously present throughout space, and the motion of grass is a direct consequence of interaction of material with this invisible field. Now, this particular image, if you are able to visualize, can offer a very helpful parallel to many complex phenomena. For example, if you consider a beam of light traveling through glass, so light here is composed of electric and magnetic fields, and you can consider this as the wind in this particular picture, and the electrons within the glass will act like the blades of grass that you have seen in the previous analogy, and these electrons will be oscillating in the response of the electromagnetic field. Now, if you could see those electrons, you will be observing them to be jiggling under the influence of the light. Now, once you understand field matter interaction, it gives you immense opportunities to do useful things with it, because now you know which way you can make your material behave with your incident electromagnetic field to give you a desired response. Just like people have used windmills to extract the energy from the wind by convert it into mechanical motion, and then eventually to other forms of energies can be stored and later assist as needed. There are many other types of fields that also can be controlled or harnessed by engineering their interaction with materials. So, this is where the field of metamaterials will be useful, that gives you control over manipulating electromagnetic fields. So, when we take materials, they are the means by which we can take hold of and manipulate the field which is otherwise invisible, right. So, that is where metamaterials belong, and they allow you to take things a step further, allowing us to create the exact kind of material response we want for a particular application, rather than relying randomly on the properties of the conventional materials and compounds which are found in nature. So, this is the best thing about metamaterial. It allows you to engineer the material to give you your desired response. Just as we could fashion windmills to produce power from wind rather than trying to use the grass, so we can also structure metamaterials to control fields in ways just not possible with conventional materials. So, metamaterials, in short, you can say that these are basically artificially structured materials that can be used to control and manipulate light, sound and any other physical phenomena. When I consider light, sound, I am also talking about the microwave, any other electromagnetic radiation. Okay. So, all the electromagnetic fields, acoustic fields can be manipulated using metamaterials. So, this particular figure shows you that you can group metamaterials by different professional disciplines. You can classify them as electromagnetic, acoustic, thermal and mechanical metamaterials. Okay. Although the first concept of metamaterials appeared in the field of electromagnetism, they were used in forming perfect lengths. Okay. Then some acoustic cloaking, double negative acoustic materials, thermal camouflaging. I am just naming a few. We have already discussed the different kind of applications in the initial lectures, right. So, here we will try to understand how metamaterials give us a new property which is not an average of its structural properties. So, the properties of the metamaterials are basically derived from the inherent properties of their constituent materials as well as from the geometrical arrangement of those materials. So, what is important here to understand that the physical structure plays the major role in defining how that material is going to behave. Okay. So, for a natural material, the atoms decide the overall property. In metamaterials, you have meta atoms or unit cells which tells you about the overall property. Though there are many structures that qualify as metamaterials, the most common is that of an arrangement of elements or meta atoms whose size and spacings are much smaller relative to the scale of the spatial variation of the exciting field. So, this is the main concept. Okay. The variation or the size of the spacing of the unit cells should be much smaller than the wavelength of light or any other field it is interacting with. So, in this limit, the responses of individual scatterers as well as their interactions can often be incorporated or homogenized into a continuous and effective material parameters. So, you can get epsilon effective and mu effective. Okay. The collection of discrete elements is thus replaced conceptually with a hypothetical continuous material, and this is where the concept of metamaterial looks like. So, you basically have a collection of discrete materials, but then conceptually you can think of a homogeneous hypothetical continuous material giving you effective permeability and permittivity. Now, the advantage of this homogenization process is that sophisticated and complex materials can be engineered, sometimes with properties beyond nature, beyond what nature is providing you, and it is a simple and intuitive way to do it. So, the metamaterial elements can be thought of as molecules or atoms of this artificial material that you are designing, and they can be designed and optimized by various kind of numerical methods and simulations, and people have developed the skills of making these materials over the years. So, metamaterials provide basically a path to multi-scale design, in that the properties of the metamaterial elements will be first determined and an equivalent hypothetical continuous material will be used for subsequent system designs, right. So, this fundamental question has generated an enormous amount of discussion in the metamaterial community over the years, that how you do the homogenization, right, and it has also led to countless arguments and controversies. So, initially a metamaterial was defined simply as an artificial material structured using arrays of macroscopic elements rather than atoms and molecules of conventional materials. So, these are different pictures of fabricated metamaterials. So, these are the unit cells or meta atoms, which are basically having some physical design structure, and this design basically is different from all other designs, and they are showing you different property. So, this physical structure is also important, their periodicity is also important. Okay. So, they all decide the effective permittivity and permeability of the overall material. So, this is another kind of design. So, you can understand that you can basically change this design, change the periodicity and make a material with a effective, different effective permittivity and permeability. Now, you must have seen that this macroscopic inclusions are themselves made of conventional matter, right. However, their geometric configuration, the way you design it and the way you design the periodicity, that introduces a new layer of influence, right. So, unlike natural materials whose properties primarily rise from the atomic scale interactions, you will see that in metamaterial devices, okay, the unique behavior is basically coming not only from the base material, but mainly from the shape, arrangement and the scale of their structural elements, and this is where the physical structure becomes the defining parameter of the overall properties. So, by simply altering the geometry of these inclusions, such as their shape, size, periodicity, spatial orientation, you can design new metamaterials with very unique functionalities, and that offers a very powerful design tool, okay, that can break all the limitations of conventional material science. So, here in this I have shown you the figure of 4 different types of metamaterials. The first one is basically optical cloak, which is a 3-dimensional cloak that shows you that the light rays can bend around the object and then again converge here in a way that as if this particular object does not exist in the path of the light. So, you will be able to see the things behind this object, and that is how you are cloaking or hiding this object. So, this cloak material, that the one that you have put, which allows the bending of light in a desired direction, okay, that is made of metamaterials. In this particular figure you can see this is the thermal concentrator, okay. So, it is basically a constant heat source that is applied to the left of the concentrator. The mesh is formed by streamlines of thermal flux, vertical and also the isothermal values, which are basically the horizontal lines that illustrate the deformation of the transformed thermal space, which is squeezed into the central disk, okay, over here. Similarly, you can also see there are seismic metamaterials used for sensing. So, you can have enhanced monitoring of the subsurface fluids and structures, something like fractures after injection of some contrast agents that form periodic metastructures. And you can also think of in other field something like mass separation, where anisotropic membrane that consists of isotropic cylindrical holes of radius r1 covered by a cylindrical shell, anisotropic cylindrical shell, which has got a internal radius of r1 and outer radius of r2. So, the two molecules can permeate in the membrane, okay, where one compound is directed around the core, okay, and the other one is directed towards the core, okay. So, that way you can actually see that different kind of metamaterials can be formed. So, this is something very similar to this kind of concept, not exactly, but the whole idea here is to tell you that metamaterial concept can be used across different disciplines based on your application, and the way to construct these materials remain same. And that is why it is very important to understand the concept behind the metamaterials. Okay. So, in this particular slide I will show you an illustration of the metamaterial concept, which shows a composite material that is basically formed out of some red dots. Okay. Now, these dots might be little plastic spheres, or they may be even molecules which are separated from each other by some amount of space. Okay. So, here D is marked as the interparticle separation. Now, if you attempt to investigate this material with a wave, say light or electromagnetic wave, then the wavelength corresponding to the wave indicates how much of the detailed internal structure we can resolve using that particular wave. So, then comes the wave, okay, that you are going to compare this structure with. Now, if the wavelength is on the order of or smaller than the inclusions, that is like this, okay, then we do not really see a homogeneous material, we rather see it in this form. We see it in the form of a collection of objects, right. And this is the reason why X-ray, which is typically very small to the atomic scale, okay, or you can say it is comparable, the wavelength of X-ray is comparable to the atomic scale. Okay. You basically see individual atoms, and that is why X-ray is used to study the internal structure of materials. And again, this is because X-ray wavelength can be smaller than the distances between the atoms, okay, that is there in a solid, and that is why X-ray can see individual atoms. Now, on the other hand, if you go to the other extreme, say when the wavelength is much larger than this periodicity, in that case what is happening, the wave cannot resolve the internal structure of the material, rather it will see a homogenization picture by assuming an effectively average property of the material. So, clearly you can see the material properties of the inclusions will play some important role in determining the property of this effective medium, but not only the material property, their shape and arrangement will also play an important role. So, in this particular illustration, our atoms are represented by red dots, as we mentioned. For electromagnetic waves, the red color must be like indication of, say, some index of refraction or maybe some other property, something like polarizability. And when you see the white region in the figure, that is basically the property of the space, right, there are gaps in between. So, to illustrate how the property of the collection of these inclusions get averaged out, you will see that what we have done here is to just blur those red dots, okay, and then eventually you are getting it mixed with the background which is white, until you get a uniform light red color. So, this is where the homogenization is taking place, right. So, now we understood how things are moving in that scale. So, here distinct properties are there, every individual atoms are seen, here things are getting averaged out. So, let us analyze this more precisely, right. So, if we attempt to investigate this material with a wave, let us consider the wavelength lambda, okay, and as we discussed earlier that if the wavelength is smaller than the inclusion, that is D is larger than lambda, in that case the wave is able to see a collection of objects, and here you can call this also as atomic picture. The atoms are basically represented by the little red dots that you see here. Now, if the interatomic spacing, which is D in this case, okay, no, not D, D is basically the periodicity, okay, interatomic space will be this space, okay. So, this is nothing but D is basically the diameter of the atoms plus the periodicity, okay. So, if the interatomic spacing is again found to be in the order of the incident wavelength, you will see that the unit cells will start resonating, and you will get the concept of resonating metamaterial. Now, on the other hand, if you see from this side, we just saw that if lambda is much larger than d, the wave is unable to resolve any internal structure of this material, and rather it will give you effectively average property, right. So, what happens in between? So, this is where the homogenization picture takes place, this is where the atomic picture is, okay. Then there is something in between, okay. So, what is this in between? If the spacing between the atoms is found to be in the order of wavelength, that is, you can say d is order of lambda by 5, then the properties of the collection of the inclusions will average. As we did was to blur the red spot, okay, all those red dots were made blurred, and then they were basically getting mixed to give you that uniform light red color, right. So, it does it look very simple, but it is essentially not very simple, okay. So, the question is, can you just average the property of the molecules or some collection of objects the way an artist can simply blend the colors? In fact, if you will be wondering that sometimes things become very easy, it is that simple. However, in general, obtaining a homogeneous property from microscopic properties could be little tricky as well. So, in such cases, many researchers have considered this problem, which is also known as effective medium theory or homogenization, and that is discussed in different areas of physics. Now, these theories often will take the form of mathematical formulas that apply to fairly specific arrangement of objects, such as say a cubic array of dielectric or metallic spheres, for example, right. So, with that effective medium theory, you can always try to approximate a periodic array of meta atoms, which is nothing but your metamaterials, to be represented with a effective permittivity and permeability, okay, and that is where the concept of metamaterial will be useful, right. So, what do we require to make this metamaterial concept more useful and to be used as an engineering tool? We basically require a technique that allows one to determine the homogeneous properties of any collection of objects or unit cells, regardless of their shape and the material composition, and we will use this kind of and discuss this kind of engineering tools in the upcoming lectures in this course, and we will see how we can use this simple theory to get this kind of homogenization or equivalent homogeneous medium properties from a layer of matter atoms periodically repeated. That is basically the metamaterials. Okay. So, now let us also look into a bigger picture of all types of engineered materials, and we will see when we do the classification where exactly metamaterials fit in there. So, engineered materials, as you all know, are basically materials which are purposely tailored to exhibit some useful and enabling electromagnetic properties. So, you start with ordinary materials, which are basically the pure materials found in nature, or you can synthesize them in lab. Okay. Now, based on solely the atomic scale phenomena, you can break them in different subcategories, something like conductor, dielectrics, magnetics, absorbers, and so on. You can also take these ordinary materials and mix them up in different proportions, and that will be mixtures where the properties are also getting mixed. Okay. So, you can combine and can get some average properties for the dielectrics, magnetics, absorbers, and magnetodielectrics. Okay. Now, these two are kind of you can correlate, because the average properties are kind of mix match of the ordinary materials properties. But then comes the metamaterial, which are basically the composite materials designed to provide some properties which are not at all supported by this two class. Okay. So, you can think of a resonant type of metamaterial or non-resonant type of metamaterials giving you, resonant type can give you double positive, single negative, it can be negative mu or negative epsilon material, it can have both negative, so you will get negative index material, you can have epsilon near 0 material, super absorber, nonlinear, bi and chiral kind of material. For non-resonant type, you can have anisotropic and hyperbolic kind of materials. So, this is the classification of metamaterials. Again, you can also think of photonic crystals. Few people also consider them as a part of metamaterials, because these are also periodic structures that can fine tune the light matter interaction. Okay. Here the electromagnetic waves basically behave in a periodic photonic structure. In the same manner, electrons behave in semiconductors. So, here you can engineer the complete band gap or partial band gap of this material. Okay. So, you are actually able to tune or tailor some of the properties. So, we can also see the classification by size and frequency. Yeah, this particular slide shows you a photonic band diagram where you have the normalized frequency omega a by c on the y axis, and you have block wave vector b on the x axis. So, this is typical band diagram. Okay, but why we are interested here is to see that in the case of photonic crystals, the lattice periodicity A is basically of the order of lambda by 2. Okay. So, this is the case of photonic crystals. So, photonic crystals are basically from here to here. Okay. Now, when we talk about resonant metamaterials, the periodicity A is of the order of lambda by 10. So, you can see resonant wavelengths are kind of here. So, in this particular resonant metamaterials, the unit cells or elements are basically resonating. In the case of photonic crystals, the array are resonating, right. So, in the case of resonant metamaterials, what is happening? The elements or the unit cells are resonating. So, the new properties basically emerge from the resonance and the interference between the unit cells. You also have non-resonant metamaterials where the periodicity is much smaller than lambda by 4, and that is basically in this region. Okay. So, here the effective property derive from the averages of the constituent materials, right. So, this is where your non-resonant metamaterials lie, and then you have mixtures where the periodicity is much smaller than lambda by 10. Okay. So, you just mix up the materials, and in ordinary material you have periodicity of the order of the unit cell dimensions, right. So, this is where in this particular diagram the ordinary materials and the mixtures lie. So, this I believe all of you have seen this earlier, that the blue lines that basically tell you about the band diagram, okay, and these dashed lines tell you the light line, that is if that periodic crystal would have been replaced by a homogeneous medium, how the bands would have behaved. So, you can see that the gap in the blue lines, these are basically telling you about the band gap and so on. But here why I have put everything together, just to tell you that what is the scale comparable to the wavelength, that tells you whether the thing that you have made is a photonic crystal, or is it a resonant metamaterial or a non-resonant metamaterial, or it is a mixture or ordinary material. Okay. So, this particular relation of the size and the periodicity of the unit cell with the lambda or the wavelength of the interacting light or electromagnetic wave is very important. So, with that we will conclude this lecture. We will discuss the optical properties of metals and dielectrics in the next lecture. So, if you have got any queries on this lecture, you can drop an email to this email address mentioning the lecture title and the course number on the subject line. Thank you.